Hello, everyone. Welcome to the first virtual SI session. I'm Isaiah,
Hi everyone, I'm Hassib.
and today we will be going over motion diagrams. So Hassib will start explaining why this slope of a line in distance versus time graph is a velocity versus time graph. Then we'll go on to the transformation. Finally, we'll start some practice problems.
Okay, so the first idea that we're going to go over is why the slope of the line in a distance versus time graph is velocity. So as we all know, we all know how the distance versus time graph looks like. We have the y-axis, we have the x-axis. The x-axis usually indicates time, and y-axis is distance with however units we're going to use. And let's say we have an object that is moving and it's covering equal amounts of distance across equal time intervals. All right, so that will be our line for that object. Now our question is, why the slope of the line is velocity? Like, okay, let's see how we can get the slope in the first place and see how would that equal to velocity. So as we all know from our math classes, if this should be like a question where we can ask you guys, but nobody's here yet. The slope of the line is the rise over the run. So this is my rise. And this is the run. And we know that we can calculate the rise by subtracting the highest point, we'll call it y2, from the lowest point, which is y1. So we'll say on the side, slope equal to, and we said rise is y2 minus y1 over the run. The run is the 2 points. The furthest is x2, and the closest here is x1. So our run will be x2 minus x1. But I'm going to take this and we're going to put it in a bigger picture. So the difference in the y, based on our graph, the difference in the y would represent distance. So we have distance in here, because we represent distance on our y-axis. So any difference between 2 points along the y-axis would represent distance covered. And the difference between the 2 points on the x-axis will be time, because our x-axis represents time. But we look at this equation that we got from the slope, and we go, oh, this looks familiar. This is our equation for velocity. Then we can sit and talk if this is actually velocity, or this is including the direction or not including direction. But the general idea is, from the slope of the line of distance and time graph, we will get the law for velocity. Now we could move to the next idea. As we've seen in many of our classes lately, the professor was showing a lot of graphs on the slides of position and time and velocity and time graphs. And one thing that we have to learn in this class is knowing how to transform from one graph to the other, and vice versa. So if if in a test or a quiz, if we were giving the position and time graph, the professor could ask us to draw the velocity and time graph, or she could give us the velocity and time graph and ask us to get the position out of it. So you guys have a worksheet in the class from last week, and we're gonna go over some of these problems. So this is the first problem. It says, for each position time graph, calculate the plot speed on the speed time graph to the right. As I just said, this is a question where we have to transform position versus time to velocity versus time. Okay, that's the first one we're going to work with. The bicycle trip through hilly country. So the information given us to here is our position and time graph. This position and time graph should represent a bicycle trip. A useful thing to do before jotting down any information is usually to look at the graph and kind of get an idea of what's happening in real life, given the data in the graph. So here we can also notice that this graph is divided into blocks, and those blocks are useful because the slope in block 1 is constant, the slope in block 2 is constant, the slope in block 3 is constant, slope in block 4 is constant. So that's actually something that we keep note of. We can always divide the graph into blocks where slopes are constant. Okay, we can go back to the real life understanding. So it's a bicycle trip. So since the position is increasing over time, so it looks like that the person is moving with the bicycle. Then that's in block 1. Then in block 2, we notice that the position doesn't change. That means that the person stopped from second number 1 to second 1.5. And no change in position happened in block 2. Then we look at block 3, and we notice that it started from position 30, and it started from position 15, and it ended at position 30. So the position changed across time. That means there is velocity. And in block 4, we notice that the positions changed again from 30 to 40 miles across time. Another further analysis we can do before jotting down information, maybe we can ask, what's the difference between block 3 and block 4? We know that in block 3, the person changed their position. We know in block 4 that the person changed their position, but what's the difference between them? Well, here it's the slope. We can see that this line is a little bit flatter than this line. That means the change in position was quicker in block 3 versus in block 4. And that should indicate something to us. It should tell us maybe, oh, the speed in block 3 is different than the speed in block 4. We can also know even a little bit more information. We'll know maybe that the speed in block 3 is bigger than the speed in block 4 because it covered more distance in a shorter amount of time. And we will get all to that when we do some calculations. But the main idea here is let's get the velocity and time graph. So I'm going to draw it down. Okay, so we have our graph that we need to use Actually, we forgot a very important thing here on the graph. We need to put our units for the graph. Units and what are our axes. So as usual, our x-axis is time. And that will be in seconds. Actually, no. We can notice from here, it's in hours. And the y-axis, it's velocity, and we will be measuring it in miles per hour. Okay, so since we divided our position and time graph into blocks, we will start transforming those blocks one by one from the position time graph to the velocity time graph. So block number 1 starts from 0 second to second number 1. So our block will be right here. Then we look at the block and we go, the person changed their position. That means there has to be a velocity. And since the slope is constant, our velocity should be constant. And when we say that our velocity is constant, that means it will get represented as an horizontal line on this graph. Okay, so, but where do we need to put this horizontal line? Where? Well, we need to do some calculations. So I'm gonna do some of the calculations here on the side, then it will be erased. I'm gonna do it for each block, then I'm gonna erase it after. So for block 1, we can look a little bit closer. And as we did the calculation for the slope before, that's gonna give us the velocity. We can do the same calculation here. We'll look at the graph and we'll go, oh, it's the rise, which is 15 miles over the run. And the run, that was 1 hour from 0 to 1. Here's 0, here's 1, so that was 1 hour. So that just gave us the difference. As we did earlier, y2, y1, and x1, x2. If we got the difference, we will give us 15 miles and 1 hour. So we're going to take this information from the graph and do the calculation for the velocity for block number 1. So velocity is 15 over 1, and that means it's 15 miles per hour. And we can always put the units in our velocity equation. 15 is in miles. And the denominator, which is 1, that's in hours. Okay, so 15 miles per hour. How are we going to put it on the graph? We already mentioned that it's just going to be an horizontal line. And that's because velocity is constant. So we'll go to the graph. And 15 will be right here. And we just transformed the first block from position time graph into velocity time graph. All right, let's move to the second block. The second block goes from second number 1 to 1.5. So that will be this one right here. And we'll zoom in to this one. Take off some of the garbage. Okay, in block 2, we noticed that the person or the cyclist did not change their position. Their position stayed constant for the entire time of block 2. And when I say constant, it means an horizontal line. That means they didn't change their position. That should indicate one thing, that they didn't move. Their velocity was 0. So for block 2, we should have 0 velocity. That means the velocity will be right here. And that was block 2. Block 3. Block 3 was from 1.5 seconds until 3 seconds. So we'll get to this part right here. We'll do a very similar, not very similar, it's actually the same analysis that we did on block 1. Let's find the slope of block 2. So this is the slope for block 2. We'll calculate it this way. We should notice the same thing that we noticed on block 1, that the slope is constant. That means our velocity is going to be constant. And since our velocity is constant, it's going to be represented in an horizontal line. So we'll take the rise, or we can call it the height. And we can easily find it from the graph. It's 30 minus 15. And that should give us 15. And of course, that's 15 miles. And the run, it's the difference in time. 3 minus 1.5. And that should give us 1.5 hours. And again, my units, I get them from my axis. So you can see I'm using hours here. It should be hours right here. I have miles. It's miles right here. So we got the rise, we got the run. Let's go calculate it. So I'm gonna get rid of the old calculations. And I'm gonna call my velocity for block 3, V3. And that will be equal to distance over time. And as we said, that's the same as the rise over the run. So the rise was 15 and the run was 1.5. So we have 15 divided by 1.5. That should give us 10. I'm gonna write it. So our velocity for block 3 is gonna be 10. And if anybody was confused about the units, always go back to the law and jot down your units. So the 15 was in miles, right here. And the 1.5 was in hours. So it's 10 miles per hour. All right, we'll take that number and we'll put it on the velocity and time graph. So it's 10, it will be right here. That's V3. And that was our velocity for block 3. Right now, let's look at block 4. For block 4, we do similar analysis. We need to find the velocity. It's constant slope, so our velocity is constant. Our rise is 10 miles. And the run, it's 5.25 minus 3. So that's 2.25 hours. We can move a little bit faster with the explanation right now. Take those two numbers, divide them, and we should get the velocity that we want for block 4. Should get, again, it's distance over time. And I need the numbers. That's 10 over 2.25. As usual, that's miles over hours. And that should give us approximately 4 miles per hour. It's a little bit more. It's 4 point something, but since we're putting it on a graph, the accurate number doesn't matter as much as putting it on the correct position on the graph. So our block number 4 ends at 5.25 right here. And our speed was around 4 miles, so 5 is right here, so it's a little bit before 5. That should be our V4. And that was problem number 1. Okay, so a couple things to take note of for problem number 1. As we noticed that, let's look at the lines that have slopes in block 1, block 3, and block 4. One thing we did is that we said constant slope means constant velocity. It's a horizontal line for each block. But what does a higher slope means? So we can notice that in block 1, the line had a higher slope than block 3, and block 3's line had a higher slope than block 4. This transformed to having higher velocity. So we can notice the velocity for block 1 was around 15. The velocity for block 3 was at 10, and the velocity for block 4 was around 4. So the higher slope represented higher velocity. The lower slope, the relatively lower slope, represented lower velocity. So we have to pay close attention to that, because that's usually something good to pick up on mistakes and find if a person did any mistakes. Okay, we'll move to the second problem. Again, the second problem is another transformation from position versus time to velocity versus time. Here we did not divide anything into blocks. So guess what? We're gonna do it. So we'll look at the blocks that have constant slope, and we will see it right here. So we have block number 1, we have block number 2, block number, nope, made a mistake. block number 3 will be till right here. Block number 4. This is block number 5. And block number 6 is right here. And for the people in this section that didn't get this worksheet, this is a worksheet that was given to the other section with the problems that they need to go over with the section at 3 p.m. I don't think we were given this worksheet yet. So you guys will probably get it next class. Okay, so what I'm gonna do right now is do it quickly, because we explained a lot of things in detail in the first one. So we're going to be following a very similar process in this one. I'm going to do very minimal calculations, very minimal writing, because the worksheet doesn't give any space for calculations. It's just transforming this graph into the other graph. So I'm going to zoom into the picture and go about it this way. Okay, for block number 1, I'm going to divide the velocity and time graph to my blocks too, so I don't have to deal with it. I have 1, 2, 3, 4, 5, and 6 blocks. Okay, we can notice that block number 1 is already done for us. But we can verify. So we can come here to this block. We have the rise over the run. It looks like our rise is 200. And it's 200 meters. And the run is 5 minutes. So 200 divided by 5 is 40. And that means it's 40 meters. 40 meters per minute. And we noticed that, oh, the line was put at 20. So maybe we did something wrong. $200 divided by 5. Isaiah?
So, yeah, it seems like the line is incorrect. So, yeah, it is on 40. It should be on 40 rather than 20.
Yeah. Okay, so as we've seen, it doesn't harm to do work that is already done, so you can verify stuff. You'll be the students telling the professor, oh, your paper is wrong. So this line should be at 40. And again, it's 200 divided by 5. So that was quick. Block number 2, we should know it by now. The person did not change their position from minute 5 to minute 10. What does that mean? 0 velocity, nothing on the velocity line. Block 3, we'll do a similar analysis. The rise over the run. The rise is from 200 to this here is 600. From 200 to 650. So we'll take the difference, and that will give us that will give us 450. Because this point right here is 650. Of course, that's meters. And the time taken to achieve that distance was 10 minutes. It's 20 minus 10. So 10 minutes right here. And we do what we do usually. Divide 450 by 10. We will get 45 meters per minute. And that's for block number 3. 45 meters per minute will be right here. All right, let's move on to block number 4. In block number 4, we see a very slight change of position because the slope is not very big. It's flatter than block 3, so we shouldn't expect a very big number for speed. So again, the rise is from 700 to 800. That will give us 100. And for the run is 10 minutes. I just noticed that we did a mistake a little bit earlier in block 3. I counted this point to be 650, but actually it's 700. So we'll do the calculation again. It's 700 divided by 10. That's 70. That means it's 70. No, it's 700 minus 200. So we'll get 500 for the rise. 500 divided by 10 is 50. So instead of this line being at 45, it should be at 50. From this mistake, we can notice that it's very easy to confuse your numbers on the axis. So you have to pay very close attention to the numbers you're using, especially if they are not marked on one of the axes. I personally did this mistake way before in some of my physics classes and math classes too. So we're all in the same boat. So we'll go back to block 4. The rise was 100 from 700 to 800. And the run was 10 minutes. So 100 divided by 10, that's 10 meters per minute. So, and that's expected. We said that the line is a little bit flat, so the speed, we shouldn't expect big numbers for the speed. And we definitely got a small number, 10 meters per minute. Now we'll move to block number 5. Block number 5 will start from here as usual. And a quick glance on block number 5 should reveal what the velocity should be. Position did not change. That means velocity was 0. So in block 5, our velocity will be 0. Then in block 6, we notice a line that is not similar to the other lines. If we looked at the lines in the previous blocks, they're all pointing upwards. But with this one, this line is going down. What does that mean? It looks like that the person started at position number 0, and it went all the way to a point that is 800 meters away from the person's initial position. Then after a little bit of wait in block 5, where the person did not change their position, they went all the way back to their initial position. So that should also tell us something, that this meters right here, or position, is not distance, it's displacement. It comes with direction. So by us saying velocity, we are using the correct term. Velocity comes with the direction because the distance or the position we're using is displacement. And this displacement comes with the direction. All right, so let's analyze block 6. The rise will be this line right here, and the run, this one right here. So the rise is 800. It went from the point of 800 all the way to point of 0. 800 minus 0 is 800. And the time taken to do that was 60 minus, we run into the same thing. Be careful when you read the marks. 35 right here, so 60 minus 35, that's 25 minutes. So our calculation becomes 80 divided by 25 is, or not 80, 800 divided by 25 is 32. And we will be very eager to put 32 somewhere here. But we have to be careful. In this situation, when we calculate displacement, we have to start from the final point, the displacement from the final point. So I'm going to take this, I'm going to take block 5, and I'm going to draw it down here. So this is 0, this is 800, and block 5 started at second 35, or minute 35, and it ended at minute 60, which is right here. And the line was this one. That's the same one. So to calculate the rise, we need to start, we subtract as usual. We subtract 2 points, but we want to subtract the last point, the furthest point, or we want to subtract the closest point from the farthest point. So if we called this one y2, because it's further in the time, this will be y1. Our slope, or the rise of the slope, will be y2 minus y1. And our time will be x2 right here. This is x1. It will be x2 minus x1. And if we continue with this calculation, we will notice that y2 is 0 and y1 is 800. x2 is 60 and x1 is 35. And that should give us negative 800 over 25. And that should give us negative 32. So this is the slope. We get a negative slope. And why? The reason we get a negative slope is that the person who was walking had a velocity, but the direction of that velocity was opposite to the direction of his velocity initially. And because it was in the opposite direction, the person went back to their initial position. So the velocity was negative. So if we want to come here and represent it on this graph, our representation of the velocity on a positive, our representation of a positive velocity should be incorrect. So this is something to be very careful about. Although the graph doesn't allow us to represent negative velocity, 2 things could be done. We can put 32 right here and say to the professor, it's negative, or put the velocity right here and say it's in the negative direction. And the professor will know that from the position time graph, you figured it out that that velocity was negative. Or you can extend the graph in the other direction and just jot down your negative velocity at the correct position. So that will be our run for problem number 2. From what we went through so far, problem number 3, we should move very quickly in it. As we usually do, divide the graph into blocks of constant slopes. From a first glance at this position time, we notice that there is a change in the slope here and here, but it's a slight change. So you guys have to be careful when looking at the graphs and pay attention to the small changes in slope. We divide into blocks. I'm gonna do this relatively quickly because this is information that we explained it very detailed initially. So I divided everything to blocks. There you go. And I'm gonna work with them one by one. So my first block is here. I'm gonna draw the first block and jot down velocity right away. So I can see that this is 10, this is 5 minutes. We know it's in feet. The rise is 10, the run is 5. 10 divided by 5 is 2. So my velocity right here should be 2. And again, it's constant slope, so constant velocity, so horizontal line. All right, move to the next block. Rise is 50 minus 10, that's 40. And we should divide it by the run. The run is 10 minutes from 5 to 15. So 40 divided by 10 is 4. So my velocity for this block is 4. We'll move to the following block. This one right here. As we all seen earlier, a quick glance at this one. The position did not change, so my velocity is 0. We'll move to the following block. This one right here. It looks like I had this block slightly off. It should be right here. And with this block, we see the distance change from 50 all the way to 20. So we noticed right away it's a negative change in position. That will give us negative 30 for the rise. And the run for this block was, I'm gonna say from 18 right here till 25. And that should be 7 minutes. So 30 divided by 7 is, I'm gonna have to calculate that. It's 4.2 or 4.3. But remember, it's negative because the person went back closer to their initial point in the other direction. So we can, the same thing, indicate that with a line at 4.3 and say that it's in negative direction, or extend the graph. So this block is done, this is done, this is done. We write this one. Again, quick glance, velocity is 0, our position is constant, so our velocity is 0. That's this block. Then this is my next block right here. I just finished this one. We noticed that it's a very sharp slope, or a very big slope right here, because the line is pointing almost upward. Let's get the difference. Let's get the difference to get the rise. So this is 60. This is 20. 60 minus 20 is 40. And that happened across 5 minutes. So we get 40 divided by 5. That's 8. Of course, that's feet per minute. We can see that our graph doesn't allow us to draw 8. So we can put it all the way here and call this 8. Or you can draw a new graph, or a scratch paper that you're using could work too. Then we have this block is done. We're going to run to the other block. Again, position is not changing. What does that mean? 0 velocity. So our zero velocity will be here. And we'll go to the final block. We notice that the slope is negative because the person is getting back to closer to their initial position. That means they were moving in the negative direction. That means we should know that our velocity should be negative. And this block ends right here. So again, we'll do the rise over run. The rise was 60. All the way to 0. And if we're going to do this calculation, it will be 0 minus 60, because the final point is at 0 and the initial point is at 60. This is final. This is initial. And the timing was from 40 to 55. I'll do the subtraction to make everything explicit. So 55 minus 40. That's final. And this is initial. And that should give us negative 60 over 15. And that should give us negative 4 feet per minute. So we're going to represent it. It's either you can put it right here, indicate that it's negative direction, or extend the graph. So we can notice after going through 3 problems, we can start identifying the transformations from the position to time, from position time plot to velocity time very easily. Of course, it needs a little bit of practice, but there's only very limited ways you can transform it. So as long as everybody goes through every possible way we can transform it, you should get everything correctly. That was our session, our virtual session for September 16th, Sunday. Thank you everybody. Isaiah, do you have anything to say?
No, I think that covers it.
Okay. Thank you, Isaiah.
Thank you, guys.
All right, bye-bye. Till the next session.